Okay, I also, if you're gonna design lead compensators, we need to have reasonable Bode plot models. And so I also wanted to make it possible for you to do fixed sign system ID testing. Normally, we might prefer to do this using swept sign, but friction is really kind of messing with this system as far as that goes. So you can make a Bode plot by just doing 5 to 10 different um, fixed sign tests at various frequencies. And so it's basically a proportional control test where you're asking the closed loop system to track a sine wave, and then you'll compare the voltage into the plant with the output of the plant to do the transfer function. And so if I had an amplitude of 0.25 for my KP, sorry, a value of 0.25 for my KP, this amplitude, I'm going to try this at, say, 1,000. That's the sensor value that we're asking it to track, and that can go from negative 2,500 to positive 2,500. Um, and so I'm going to ask you to track something relatively kind of medium as far as amplitude goes. I'm going to do a 1 hertz frequency, and it's going to run for 500 counts. The control loop is running at 60 hertz, so that'll be, you know what, I'm going to drop that down. I'm going to drop it down to 180, so that'll be a 3-second test. And so the Zumo tries to rotate a few different times, and then here we have a sine wave with a certain amplitude for the output, a sine wave with a certain amplitude for the input, although that maybe doesn't look super sinusoidal. Um, and then there's some kind of phase lag between here and there. Now you would have to, in order to turn that into Bode data, get the magnitude ratio, which would be relatively simple, and get the phase lag. You could try to estimate that a couple of different ways, but one option would be to just truncate the data, maybe somewhere around like 100 counts, and fit one sine wave to the input and one sine wave to the output. And if you then had a mathematical expression for each waveform, you could find the magnitude ratio and the phase difference very easily from that.